RAID bonds multiple drives together to increase the available performance that a single drive can provide. RAID also adds redundancy and fault tolerance to protect against data loss. The more components any system has, the higher the probability that some components will fail. With hundreds of drives under their control, storage systems experience more drive issues than a typical PC with a single drive. Selecting the correct level of RAID technology for a system ensures customer data is adequately protected against loss. Data on a single drive in a laptop is vulnerable if the drive experiences damage or a failure. A group of a dozen laptops are as vulnerable to data loss from a drive failure as a single laptop. A dozen drives that are joined with RAID functionality can protect data against multiple types of failures. Parity is checksum information calculated from a stripe of data blocks. A damaged or missing block of data can be reconstructed from the parity information. The more parity drives that a RAID configuration uses, the more drives a RAID group can lose and remain functional. RAID configurations are classified by levels defined by the number of drives and the implementation of parity information. RAID 0 joins two or more drives together in order to stripe data across the drives. RAID 0 increases performance but provides no protection to the data. RAID 1 joins two drives together by mirroring data on the first drive onto the second drive. RAID 1 increases read performance because data can be read from either drive. Parity is not used, but the mirror provides some protection against data loss and protects against a single drive failure. RAID 2 and 3 are rarely used, so RAID 4 can be skipped. In RAID 4, one drive in a RAID group is dedicated to storing parity information. RAID 1 joins two drives together by mirroring data on the first drive onto the second drive. RAID 1 increases read performance because data can be read from either drive. Parity is not used, but the mirror provides some protection against data loss and protects against a single drive failure. For example, if a drive fails and is being rebuilt and then another drive fails, the RAID group breaks and requires use of a data recovery service to rebuild one of the failed drives. If a drive fails on Monday and is rebuilt, and then a drive fails on Wednesday, the RAID group is still protected because only one drive is in a failed state at a time. RAID 5 is similar to RAID 4. The primary difference is that the parity information is embedded in the data block stripe rather than being stored on a dedicated drive. Performance is slightly better than in RAID 4. Fault tolerance and redundancy are the same as for RAID 4. RAID 6 is implemented by extending RAID 4 to add a second parity block on a second parity drive, or by extending RAID 5 and adding a second parity block in the data stripe. An additional parity block allows for larger RAID groups, which increases performance by spreading I/O across more drives. RAID 6 protects RAID groups against the loss of two drives in the same time window. For example, if a drive fails and is rebuilding on a spare when another drive fails, the RAID group continues to function. This failure is referred to as a double drive failure. If a drive fails and is rebuilt on Monday and another drive fails on Tuesday morning, the failures affect two drives, but it is not a drive failure because only one drive is in a failed state during both failures. This animation is a simplified representation of how parity works in a RAID 4 or RAID DP implementation. Assume that each 4 kilobyte block is assigned a unique numeric value. By adding all those values together, a sum is calculated. This sum is stored in the parity block for that stripe. As shown in the illustration, one drive in the RAID group has failed. By computing the difference between the value stored in parity and the sum of all the blocks now that one block is missing, RAID determines the only value the missing block can be and reconstructs it on the spare drive. If this were an algebra equation, you would have to solve for x. This calculation is performed on every stripe until the entire drive is reconstructed. RAID-DP is NetApp's proprietary implementation of RAID 6. Diagonal parity adds a second parity value by calculating blocks on a diagonal stripe. If the system were to rely solely on the physical drives, systems with a single drive shelf and the drives on the edges would not have enough blocks to create a meaningful parity value. Therefore, RAID-DP creates an array of synthetic drives and data blocks. The value of all physical, synthetic, and parity blocks in a diagonal stripe are stored on the D parity drive. If the system only used RAID 4, the loss of 2 drives in a RAID group would result in parity calculations with too many unknown variables. You would have an algebra equation that would require you to solve for both x and y. Instead, you can use the diagonal parity to create an equation where you only have to solve for y. When you know y, then you can solve for x in the horizontal stripe. With the move to 2.5-inch drive form factors, the density of drives in a drive shelf doubled. Simultaneously, the capacity of drives has multiplied. Most drive failures are not due to mechanical issues, but to issues with the storage media. More drives of larger capacities provide more opportunities to experience an issue. For this reason, NetApp introduced a third parity drive to RAID groups. Triple or T parity works just like diagonal parity, except the diagonal stripe goes the opposite direction. The values of physical blocks, synthetic block, parity, and D parity blocks are summed and stored in the triple parity block. A third drive failure results in having to solve for X, Y, and Z in the horizontal stripes. Similar to diagonal parity, you can use the triple parity stripe to solve for Z, where only one block is missing in a triple parity stripe. This step then allows RAID to use diagonal parity to solve for Y in diagonal parity stripes. Now, there are horizontal stripes with only one missing block, so RAID can solve for X. This process continues until all 3 drives have been recovered. Recovering blocks through parity reconstruction can take a lot of time and consumes a lot of CPU resources. ONTAP and Waffle are smart enough to copy healthy data stripes to the replacement drive and only perform parity reconstruction when a data block is unreadable or the drive has physically failed. Many of the animations in this course present the functionality of RAID technology in a simplified way. Use these resources to learn more about RAID technology. RAID with parity increases performance while adding fault tolerance and redundancy. RAID-DP is NetApp's proprietary RAID implementation to protect against the loss of 2 drives in a RAID group. RAID Tech is proprietary protection against the loss of 3 drives.